In this lab, the motion of an object was captured on video and used to demonstrate constant velocity. Constant velocity is when an object's speed remains constant and the direction is unchanging. In the graph on this slide, all of these time versus position lines demonstrate constant velocity because the slope is unchanging. I chose to record a cylinder water bottle rolling in a straight line across the floor at a nearly constant rate. As I will later show, since I am not in complete control of net forces acting on the water bottle, the velocity was not exactly constant throughout, but fairly close. By using Tracker, I was able to capture the water bottle's X position over a time period of about 1.167 seconds. Tracker allowed me to extract a position versus time graph, as well as a table of data that will be used for later comparison. As you can see by the graph, the water bottle is moving at a fairly constant rate, which we know because the slope of the graph, or its velocity, hardly changes throughout. To see how accurate my observed system was in terms of constant velocity, I created a computer model which mocks the system. The model uses the observed video's constraints, including its starting position as well as velocity. When the program is run, it mimics the real-life model, producing an image, position versus time graph, as well as a data table. To calculate the velocity to use in the computer model, I used the observed data to find change in position over change in time, which I found to be around 0.8133 meters per second. By putting the data points for both the observed and the automated model in an Excel file, I was able to plot both datasets on a single graph. Here, the straight line reflects the growth script, or the expected model, while the points reflect the observed model. By analyzing this dual position versus time graph, you can see that while the computer model is fairly close to the observed model, it did not exactly predict the output. The observed data shows the object does not have an exactly constant velocity since there is a slight curve in the plot. This is likely due to the natural motion of the water bottle going slightly faster in the beginning after the initial push and then gradually slowing down after reaching a peak velocity due to the force of friction. The designated coordinate system used in Tracker could likely affect the output of the object's data. If the coordinate system were to be flipped, the water bottle would be traveling in the negative x direction. Therefore, its velocity would be negative. In this case, the graph would look slightly different because it would have a downward slope rather than upwards. In the computer model, the net force acting on the object was set equal to 0. This is because we were assuming that the water bottle was moving at a constant velocity and there were no net forces acting on the object. This does not mean, however, that no forces at all were acting on the system. This could mean that the forces canceled one another out because there were equal and opposite forces acting on the water bottle. In our observation, the initial force of pushing the water bottle would increase its velocity, causing it to speed up. However, eventually, the force of friction acting on the water bottle would slow it down, decreasing its velocity until it comes to a complete stop. This is likely why in the graph it showed a slight curve, where the velocity increased a bit in the beginning, reached its peak, and then began to decrease. In conclusion, demonstrating constant velocity is difficult to do. This is because we are not entirely in control of our system and cannot always ensure the net forces acting on an object are equal to 0. However, by using a computer model, we are in complete control of the system as well as the forces acting on it. This helps us predict our observed model as well as backcheck how accurately it displays what we are trying to capture, which in this case was constant velocity.